Okay, so let us begin. First, I'm happy to introduce the speakers today. So first of all, let me introduce myself. I'm Dr. Mayasari Lim and CEO of SE3D. And as mentioned today, we have Bowman Bagley from Advanced Biomatrix, who will be joining us and telling us a little bit more about collagen as a biomaterial for bioprinting. And with me here, I have Oliver Lai, our biochemical engineer at SE3D, who will be also talking a little bit more about the bioprinting process and also how to prepare the materials for bioprinting. So without much ado, I will turn this time over to Oliver, who will walk you through the bioprinting steps.
All right, hi guys, I'm Oliver. As Maya said, I'm the biochemical engineer at SE3D. So first of all, I just kind of want to recap a little bit about bioprinting in general. So it's really similar to a 3D printer in that you have a machine that's moving in the X, Y, and Z axes to extrude material, except instead of printing with plastic filament, we normally print with biomaterials, and these are typically hydrogels or other polymers that you can use to create cell-laden tissues and other scaffolds and structures. And then this image is just an example of using spheroids deposited layer by layer that eventually fuse into a solid biological structure. So typically in bioprinting, we use hydrogels very frequently for printing. And these are just networks of polymer chains that retain a very high water content. And typically we'll prepare these by either chemically, thermally, or photo cross-linking them. And this just maintains their network structure and makes sure that they have high mechanical strength. So in the picture on the left here, you see that the structure kind of retains its own shape. It's able to be printed onto the Petri dish directly. Whereas on the right, we have alginate, which exists in a liquid form before cross-linking. And that's something that's not as printable. So for printing soft materials that otherwise can't really hold their own shape, we can use a technique called fresh printing. And this stands for free-form reversible embedding of suspended hydrogels. And essentially what this is just a technique developed by the Adam Feinberg group at Carnegie Mellon. And instead of printing directly onto a surface in air, the entire print process is done in a temporary hydrogel support bath. So you can see in the figure that the syringe is extruding material directly into the secondary support hydrogel bath, and then the structure is able to retain its own shape without collapsing or deforming. So a little bit more about the support bath itself. So we're using a gelatin microparticle slurry. So this is just a suspension of really small particles of gelatin, and it acts as a Bingham plastic. And this means that at low shear stresses, it acts as a solid body, but at high shear stresses, it'll deform as a viscous fluid. So this allows the needle tip to move through the slurry, but as it extrudes material, it'll hold that in place to make the 3D structure. So the slurry is prepared in a buffer, so that just helps maintain cell viability. And since it's gelatin, it's also thermoreversible. So if we heat it up to 37 degrees, the gelatin will melt away and you can replace it with culture media. And today we're going to be printing with gelatin, but you can use the fresh method with a bunch of other biomaterials, including alginate, fibrin, matrigel, and others.
We're printing with collagen today.
Oh, right. Sorry. Yep. So preparing the slurry is actually pretty easy. So the first step is just to make a gelatin solution in buffered saline. And then after that, refrigerate overnight to let the gelatin set and form kind of a puck, if you will. Then you're going to blend that gelatin puck with more saline solution to create the slurry. And then after that is just to centrifuge it several times to compact the gelatin slurry and remove the supernatant. And I also want to talk real quick about our bioprinters that we've developed. So we have the Rebel X and the Rebel Mini, which we'll be printing on today. And the main characteristics are just that it uses a mechanical extrusion system, and it allows you to load and unload syringes very easily. And without further ado, I'll pass things off to Bowman, who will talk a little bit more about the LifeInk 200 that we'll be printing with.
So, Bowman, we're gonna make you the host now, and you can present your slides.
Okay, can you see the slides okay?
Yep, we can see it fine.
Okay, thank you. So my name is Bowman Bagley, and I work for Advanced Biomatrix, and I work in product and business development. So over the last couple of years, I've had the opportunity to print a lot of different things with LifeInk 200, which is a pure collagen bio ink that we've developed here, and so I'm going to discuss it a little bit here. When we look around the world, there's a lot of bioprinting companies, there's a lot of growth, a lot more publications coming out, and it's all very exciting. But what we're seeing is this lack of these native materials that can be bioprinted. There tends to be this kind of satisfaction with non-native materials. And so our company really focuses on providing highly purified native extracellular matrix proteins. And so we've turned and used that technology to create bioinks for bioprinting. And so our real mission is to focus on these native materials for bioprinting, allowing you to print materials, print tissues found in the body using the same materials that are found in the body. So the current bioinks that are currently really available are focused on cellulose technology or alginate, synthetic materials, pluronics. And if you're trying to print a human heart, then if you have it full of cellulose, then it's no longer really a human heart. So you really want, if we're trying to print human tissues, I think the material, the ink, should be full of the same native proteins as your human tissue. And so if we really look at the human body, the majority is water. But the next biggest portion is the extracellular matrix. And the two biggest components are type 1 collagen and glycosaminoglycans. And so type 1 collagen being the most abundant protein in the body, we feel that that was the best candidate for a native bioink. So we introduced LifeInk 200. And LifeInk 200 is a concentrated type 1 collagen. It's pure collagen. So there's no other additives, no other fillers. And using the fresh technique, you're really able to, for the first time, print with pure collagen. This material, when you print, it extrudes as a continuous filament. The collagen, thanks to some proprietary technology, is shear thinning, and it'll recover so that it doesn't shear your cells as you're printing. You can consistently print through a 30-gauge needle, and because it's collagen, it's extremely cell-friendly. Cells are used to being surrounded by collagen in the body, and so printing with collagen is really a natural choice. And when we start printing with collagen, you've all seen these noses and ears that are popping around, and people are printing them. But you can print these with pure collagen now, but we can also look at some slightly more applicable, tissue engineering scaffolds of different porosities and heights. And you can even go more complex with a 3D printed heart valve made out of pure collagen. So you no longer have to create these human tissues with alginate or cellulose, materials not ever found in the human body. You can print them with pure collagen. And because it's collagen, cells love it. This is an image of some fibroblasts. And you can already see they're elongating, and they begin proliferating extremely quickly in this pure type 1 collagen environment. And so the collagen LifeInk 200 in conjunction with the fresh technique really opens up a whole new level of bioprinting, and really opens up your mind to what can and can't be printed. And it's really exciting new technology. So I will send the meeting back over to Maya and Oliver to continue the presentation. Okay, Maya, I sent it to you.
Okay. So,
so I guess this slide is just a picture of the collagen scaffold being shaken in a petri dish to demonstrate that it can kind of deform under stress but recover after that once it's cross-linked. And then now we can move on to actually printing with collagen today. So the materials that we'll need are the fresh starter kit and the Lifelink 200 from Advanced Biomatrix. So this just includes everything you'll need to prepare the fresh slurry as well as the collagen itself. And then for actual bioprinting process, we'll need some plastic syringes, 30 gauge needle tips, and then petri dishes that we'll be printing into. So for actually printing with the collagen, the first step is to prepare the gelatin slurry, which I've already done and placed into the petri dishes. And then I've also loaded a 5 ml syringe with collagen. And so now we'll switch over to the webcam so we can show you the actual print process.
It's showing, yeah. So Bowman, you're all seeing the printer right now, right?
Yes.
Okay. So maybe you can show them the different components first.
So just to give you guys a sense of what the slurry actually looks like, this is just slurry that I've scooped into a petri dish, but you can see that it's very moldable. I can deform it real easy. And so this is the 5 ml syringe that I filled with collagen. I'm gonna just go ahead and load this into a bioprinter. So the syringe just slots into the extruder unit like that. And then I'll go ahead and just place our petri dish full of the fresh slurry. And if you're familiar with 3D printing, you know that normally you set the Z0 position based on the actual surface that you're printing in. But since we're using the fresh method today, we actually want the print to start suspended in the slurry. So what I'll do is just move the needle tip close to the side of the petri dish so that I can see. And then I'll actually set the Z0 position somewhere in the middle of the slurry.
So for the first model, we'll just print a simple bronchi, like a bronchi ring. And just to show you, it's a little bit hard to see from the camera, but once it's finished printing, we'll show you from the top view the structure that is being printed. Also, there was a question about the printing temperature of Lifelink 200 in chat, which Bowman had already addressed, but I thought it might be good to just share it with the group over the webinar. So, so Bowman, would you like to kind of just address those questions?
Yeah, so Lifelink 200 prints at room temperature, and you can actually see it printing right now on Maya's screen, or I guess on all of your screens. So this is printing at room temperature. Oh, Maya, can you actually mute everybody?
Yeah. So I'm not muted yet. Yep. Okay, so I think folks, yeah, everyone is muted, I think. All right.
And then can you unmute me, or am I unmuted?
Yeah, you're unmuted.
Okay, perfect.
And then the second question was whether it can be printed in air without using the fresh technique.
Thanks. So if you try to print this material in air, it's going to, after you do a couple layers, it's going to kind of start sagging on itself, and it'll start kind of running. The Lifing 200 is kind of like the consistency of toothpaste, but if you print in air, it'll kind of start running. When you print into the fresh, it forms these really nice, the filaments come out as these really nice continuous filaments, and because it's kind of like a zero weight environment being inside the gelatin slurry, the collagen is essentially suspended, and so the material won't run anywhere, and then you're able to then create those complex structures. And then after you're done printing, you simply incubate. For example, in the video, there's the 35 millimeter dish. You simply incubate that dish at 37 degrees for about a half an hour, and the gelatin will fully melt at 37 degrees, go completely into a solution, and your collagen will further polymerize, and your construct will be just floating in the melted gelatin slurry. And then at that point, you just simply replace the melted gelatin slurry with your cell culture medium, add your CO2, and you're ready to continue the cell culture process of your cells within the printed construct.
Great, thanks. So if you have any other questions, I would encourage you to type it into the chat box so that won't be too many background noise from the other participants. So I think some of you can probably see the ring structure forming from the camera. And this is, how many millimeters are we printing on this one? The height. Maybe about 5 millimeter in terms of a height of a ring.
Just as another note, the picture of the nose that I showed was about it was about 100 layers tall of printing. Just kind of each layer is about 0.1, so it's about 10 millimeters tall. But the printer did a full 100 cycles or 100 layers to print that nose.
Right. So here, just also to note, we're using a very thin needle gauge. This is a 30 gauge needle, which is about a 160 micron diameter resolution. So the printing process is a little bit slower here because we're printing at very fine resolution. We have a few other scaffolds that we will also show you all. So just to give you a sense of the rigidity or the flexibility of these materials, they're pretty soft materials.
Right, so this print is done, and just because of the slurry, it's kind of hard to see, but you can see that it printed the kind of ring structure here.
And then we can show the other scaffolds.
And then this is a kind of scaffold shape that we printed just a few minutes before the webinar. And finally, we have some cross-linked collagen samples that we can now suspend in just water. Since they're cross-linked, they'll just kind of retain their shape indefinitely. So this is a meniscus structure from the knee that we printed.
This is just the same scaffold. Yeah. Do we want to do? Are there any other questions? Oh, so there's another question about how different is Lifing 200 compared to decellularized ECM bioinks available in the market in terms of printability or biocompatibility? Bowman, would you like to address that question?
Sure. I think the decellularized ECMs, kind of bioinks, they have some really neat potential. I think right now there's a lot of tissue-to-tissue variability in terms of where you're getting your ECM. If you're having like a decellularized heart ECM, there's just a lot of variability right now. And so our focus is really on these highly purified materials so that you get consistent results and lot-to-lot consistency, highly purified. I have not printed with any of the decellularized ECM bioinks at this point, so I can't talk on the printability of them. But if you send me a link to where you can get some, then I'll be more than happy to start testing some out for you.
Great. And another question for you, Bo, is where can we get the fresh material?
So right now you essentially you make your own fresh material in the lab, and so there's a starter kit that's available that comes with the gelatin, the various jars that you'll need, and very detailed instructions in the videos and even the blender. And we're currently working on creating a finalized product where you will be able to you won't have to go through all those steps. It'll just be ready to go and ready to print into when you buy it. And so since that product's not fully ready, the kind of in-between product is what we call the fresh starter kit. And so as you can see, Oliver at SE3D has mastered how to make it. It's kind of it's not too bad of a process. And so me or even Oliver would be more than happy to walk you through how to make the material and how to begin fresh printing in your lab. So we're more than happy to take the time to help you figure that out and to begin printing with fresh.
Yeah, and at the moment you already have a lot of videos that you provide on your YouTube channel as well, right, Bo?
Yeah. So if you go, when you buy so they're all on our YouTube channel, but also they're embedded within the directions for use on how to make the fresh slurry. And so I can send that directions to use to anybody that's interested.
Yep. So and here at SE3D, we also do sell the fresh through our partnership with Advanced Biomatrix. So if you guys purchase our printer, you could also purchase the inks, the complementary inks, whether it's fresh and the collagen through us as well. So it's just one transaction, and we'll be partnering with ABM to provide you with all of the materials. We will also have a portal that provides you with all of the printing instructions, videos, and user guide, and all of those materials on our website as well. So that's something that will also be very useful in terms of resources for you to learn how to print with different materials and different techniques. So I'll be happy to share the portal information with you all after the webinar. Another question, I guess for Oliver, for us, is what is the print speed and resolution usually used for these biomaterials? So Oliver, maybe you want to talk a bit about the print speed?
I think in this case, our print speed is 10 millimeters per second. So typically, the faster you go, the more prone you are to misprints. So somewhere around this range is usually what we go with. And then the resolution, it'll just kind of depend on your needle tip. So in this case, we're printing with a 30 gauge, which is an inner diameter of 160 microns or so. And typically you can go down to maybe around 150 microns with special metal tips. It'll also depend on the material you're printing with, how easy it is to extrude through a needle tip and whatnot.
So right now we're printing another scaffold, which Oliver showed you earlier, but we will just demonstrate the printing process, and you can kind of observe the resolution of the prints after the print is done.
Yeah, Oliver, can you hold up the hexagonal shape that you showed earlier?
Yep, I think so.
And is that what you're printing right now as well?
Yep, that's what we're printing.
Very cool. Thanks.
Maybe I have a question for Bowman. Bo, from your experience, what has been some of like the biggest challenges printing with collagen, since you have a lot more experience than us on printing with collagen?
So the reason why most people don't print with collagen right now is because historically the collagen molecule is actually it's temperature sensitive, and it's a very soft. It forms really soft hydrogels. So we've been able to modify, or using there's one proprietary method, but another method is this material is about 35 mg per mil concentration. So it's highly concentrated, and then there's also one other step that allows it to be shear thinning. And so this material right now, it's like I said earlier, it's kind of like a toothpaste consistency, and it allows it to, and the way it's formulated allows it to actually be stable at room temperature, whereas previously collagen materials have to be kept at about 4 degrees Celsius, or else they'll gel and clog your needles. And so this material can be printed at room temperature, and it won't gel and clog your needle. And so that's really overcoming that one hurdle. And then the fact that it's at the concentration allows it comes out as these continuous filaments, and the shear thinning also really helps it come out as these continuous filaments that kind of stick together and help stack and build these structures when printing in fresh. And so there's kind of two innovative technologies built into this one ink that allows collagen to be printed like it's really never been printed before. And so if you buy the material, the Lithing 200, when you get the syringe, it's already pH neutral and it's already isotonic. And so you could literally just add your cells directly to the collagen when you get it as it is. You don't have to do any additional preparation steps in terms of titrations, pH adjustments, or adding the salts or anything like that. It's ready to go. And that's previously never really been possible. And so that's why we see a lot of these other materials that are being printed with, because they're easier. But now that's why we came up with this product.
Okay, great. Thanks for the background information. So if I wanted to like mix this with cells, that shouldn't be any issue. Any kind of cells should grow pretty well in the collagen ink that you have, right?
So we haven't tested all the cells, right? There's tons, but we've tested adipose-derived stem cells, chondrocytes, fibroblasts, some epithelial cells, and so we're trying to continue to test more and more, and we have some collaborators using more cells. We've done mesenchymal stem cells. So I don't want to come out and say that it'll work for every application for every single cell type, because there's just no ink that does that. But most cells in the body are surrounded by collagen, and so this is a good choice.
Okay. Do you normally do like a 1-to-1 ratio for the cell to collagen?
No, you'll end up it starts at about 35 mg per mil, and the recommended concentration, we recommend diluting it to about 24 mg per mil.
Okay.
That seemed to be kind of the best for collagen concentration and cell viability.
Got it. Okay. Okay. Sanjay has a question about how do you store the collagen syringe and what is the shelf life? So
when you get the syringe, you store it at 2 to 10 degrees Celsius. So you just put it in your refrigerator, and the shelf life from the day you get it will be it'll be at least 2 years.
It's pretty long time. Another question I have for you, Bo, is it possible to align the fibers on collagen as you're printing it, or is there any techniques we could do to like induce alignment of the fibers?
So we've been looking at that recently, and we've seen partial alignment, and just simply based on the shear as it goes to the needle. And so the way to increase that alignment would be using smaller diameter needles, higher pressure, and faster print speeds. And we're seeing partial alignment, but we haven't investigated it enough to try to get fully aligned fibrils. But there is evidence of some alignment, but it really depends on those three variables.
Great. There it is. It's done. So that took about 8 minutes, maybe?
Yeah, more or less.
About 8 minutes, yeah. So it wasn't too long.
It doesn't look like it used that much ink as well.
Yeah, I think it only used about 1 mil, probably, right, Oliver? Because we printed
less than that.
Less than that, yeah. Because we printed something else before. We printed 3 scaffolds on this one syringe already. So yeah, so pretty straightforward. Yep, that's the final. Okay. So anybody have other questions? Okay, there's another question. Okay, another question is, can Live Ink 200 be filtered in a 0.22 micron filter at the 35 milligrams per mil concentration, Bo?
So the product is already sterile, and so you won't need to filter it.
And another question, would you consider custom batch orders of specific structures of approximately 100 units? Bo?
That might be more of a question for you, Maya.
Oh, really?
I think the question is asking for the actual structures already pre-printed.
Oh, I see. Okay. Okay. So is that right, Penny? Is that the question, that you wanted, I guess, pre-printed structures of these scaffolds? Yes. Okay. Yeah, I guess it's possible for us to pre-print these structures and ship it out to you in batch orders. I think shipping shouldn't be a problem, Bo, right? Like in room temperature, once we print the scaffolds, have you had any issues of shipping them?
So I have printed a couple scaffolds, and the way that I do it is I print it directly into the fresh, and then because it's gelatin, it's solid in the when it's cold, and so I put the scaffold in the refrigerator, and then you can then ship it, and then the customer would then you would then get the scaffold and then incubate it to melt the gelatin and release your scaffold.
Yeah, that's right. Okay. Yeah. So yes, Penny. So that will be definitely possible. You could definitely email me, and we could connect and talk more about that. Okay. Any last 1 or 2 questions before we close the session? And I will definitely provide the recording to everyone so that you could review it in the event you'd like to review the video again. Okay, so if there is no other questions, we would like to thank everyone today for joining us in this webinar. We welcome your feedback, so I will be sending you an email and asking you to give us some feedback to help us improve on our upcoming webinars. And also, you have other topics or things that you'd like us to cover in the area of bioprinting biomaterials or other techniques, feel free to email us and reach out to us and let us know what you'd like to see. For our next webinar, we will actually be featuring bioreactors as a post-printing solution. So we will talk a little bit about the different options you may have in the market of bioreactors. And then specifically, we have a partner who is also providing a very novel bioreactor that I'd like to share with all of you. So do look out for the next webinar. We'd love for you to join us, and we will be happy to go into more details about 3D bioreactors for tissue engineering and 3D cell culture. So thank you again, everyone, for joining us. I will see you soon, hopefully, in the virtually or in person someday. Thanks, Bo.
Hey, thank you, Maya. Appreciate it.
All right, take care. See you.